Planets and stars have a ceiling, a point where physics simply won't let them get any bigger. Black holes aren't bound by those rules. They have no physical size limit and can grow without stopping, expanding as long as matter exists. Even at the bottom of the scale, the proportions are difficult to wrap your head around. If primordial black holes exist, they date back to the Big Bang. One of these could hold 1 trillion kilograms, the mass of a mountain, packed into a space no larger than a single proton. The black holes they've confirmed are out there, like stellar black holes, form through collapse. When a massive star runs out of fuel, its core is crushed under its own gravity until it reaches a point of no return. These are often compact. M33X7 has nearly 16 times the mass of our Sun, yet it is only about 92 kilometers wide. If it were placed over the Mediterranean, it would be just large enough to cast a shadow on the island of Corsica. This establishes the basic rule of the cosmos. Black holes are gravitational sinks that get larger the more they eat. This chart shows the frequency of black holes we've observed compared to their mass. We see a steady population up to about 150 times the mass of our Sun, but then we hit a sheer drop-off. For a long stretch, the data goes completely blank. But looking further up the scale, the population suddenly reappears. We find black holes millions of times more massive, with nothing to explain how they got there. This presents a problem of time. For a stellar black hole to reach these sizes by eating stars and merging, it needs billions of years. The universe simply isn't old enough for them to have grown this large through traditional means. The model of slow, steady growth doesn't explain these giants. Their existence suggests that the rules of physics required a different mechanism to jumpstart their development. To find that mechanism, we have to look back at the early universe, where matter was packed much more densely than it is today. This environment could have fostered the growth of quasi-stars.
Are the likely origin of the supermassive objects we see anchoring galaxies today. At the center of our own Milky Way sits Sagittarius A star, a supermassive black hole with 4 million solar masses. Compared to what's coming, it's relatively quiet. While we often think of these as the anchors of their galaxies, they usually only make up 0.001% of a galaxy's mass. It's actually the gravitational effect of dark matter that holds the billions of stars together. But the sheer physical volume is staggering. The black hole in the galaxy Cygnus A is 14.7 billion kilometers wide. If it replaced our Sun, it would swallow every planet and stretch halfway to the edge of our solar system. The black hole in Messier 87, with 6.5 billion solar masses, provided the data for this image. It is the first direct visual evidence that these massive entities actually exist. Further up are the ultramassive black holes. OJ 287 is so large, 18 billion solar masses, that it has another supermassive black hole orbiting around it. At the top of the scale sits TON 618. It holds 66 billion solar masses. It is so wide that it would take a beam of light a full week to cross from the event horizon to the center. You could fit 11 solar systems side by side inside of it. At this scale, everything we know about our corner of space is reduced to the size of dust. These ultramassive objects are some of the most stable structures in the cosmos. Because they take so long to decay, they will likely remain long after the last stars in the universe have burned out. But there is a catch. How do we accurately measure the weight and size of something that is, by definition, invisible? By watching nearby stars whip around an empty point in space, we use Kepler's laws to estimate mass. To find the physical diameter, we use the Schwarzschild equation, but that math assumes perfectly round, stationary black holes, conditions that don't exist in reality.
These assumptions mean that the numbers we use for objects like TON 618 come with significant uncertainties. They are estimates, not exact coordinates. Given the limits of our math and our small perspective, the scale of TON 618 is likely just a baseline. The true largest object in the universe is almost certainly still out there, waiting to be found.